All right. Now, up to now, we have learned how to find the surface temperature of the star and the distance of the star from Earth, right? Today, we are going to basically find the radius of the star using Stefan Boltzmann law. Now, you should write that Stefan Boltzmann's law states that the total energy transmitted total energy transmitted against fact let's not write like emitted, that's better. Can't transmit. Emitted by a black body per unit area per second is proportional to the fourth power of the absolute temperature of the body. Okay. Writing fourth power is very, very important. Now, basically what he said was that luminosity is equal to 4 pi r square. So 4 pi r square is the surface area, okay? Times Stefan Boltzmann constant times the temperature raised to power 4, like that. Okay. Now, from this we know that, okay, wait, let me just put it this way, luminosity of star in watts. This is basically the radius of star in meters. This is Stefan Boltzmann constant. This will be given to you in the exam, so don't have to worry about that at all. The value of this is 5.67 times 10 raised to a minus 8 watts meter minus 4 Kelvin minus 2 Kelvin minus 4. And this is the surface temperature in kelvins, right? So this is the formula. Now, what I'm saying is, remember from this relationship, we've learned that luminosity depends on, number one, surface temperature, number two, radius. Okay, remember that. Okay, now Now, what you need to understand is that the flow of everything basically comes together here by basically of how we can actually find the radius of star. So I'm going to write the flow so you guys can actually relate to it later on. Wait a second, let me this is thicker. Estimating the radius of a star. Now, so first of all, remember that we use F equals to luminosity over 4 pi d square. That's the formula that we know from the distance, right? Then from this we can actually find, because we know the distance, we can find the luminosity or the distance, whatever is required, doesn't really matter. From this one we go towards the next equation, which is the Wien's displacement law, which is 1 upon time period. So from this we find the temperature, right? And from here we use the third equation, because we now have the temperature and the luminosity. And then from here we find, basically we use the Stefan-Boltzmann law to find the radius of the star. Okay, because I'll just write it. To find luminosity, this is to find surface temperature, and then to find the radius. So each property one by one we can find through these equations. If you realize that, that's what we're doing in a flow. Is that clear? Suman, Nadia, Gatika, and Aman, any questions? Okay, now let's do a worked example here, and then we'll go forward. Question.
So what is d4 in the first equation?
This is the distance of star. Should I write that too, or the whole thing?
No, it's fine.
Okay, because I wrote it earlier, that's why I did not write it here. So the question is that Betelgeuse is our nearest red giant star. Oh crap. Wait a second. One mistake and now it starts to sync. Betelgeuse is a nearest red giant star. It has a luminosity of 4.49 times 10 raised to power 31 watts and emits radiation with a peak wavelength of 850 nanometers. It says calculate the ratio of the radius of Betelgeuse RB to the radius of Sun RS, and they've given the radius of Sun Rs equals to 6.95 times 10 raised to 8 meters. All right, can you guys do it, please? Okay. Okay, done. Should I go forward then? Any answers, please? You guys so slow. Okay. So first of all, everybody, you need to find basically from 4 pi r square, Stephen Boltzmann constant time raised to power 4. You need to basically use this. You need r b right here. So what you're gonna do is you need temperature, because we don't have the temperature, right? We have the luminosity. So for temperature, you can find that lambda max, which is we have the maximum wavelength, the peak one, is equal to 2.9 times 10 raised to power 3 minus 3 mk, right? So this is that. So we can find the temperature by dividing this by 850 times 10 raised to minus 9. From here, we should be getting 3410 Kelvin. Is that correct? Then what you do is, to find RB, luminosity was given as 4.49 times 10 raised to 31 multiplied by, sorry, we don't need to multiply, divided by 4 pi, and Stefan Boltzmann constant was 5.67 times 10 raised to minus 8 multiplied by this temperature 3410 raised to power 4, and then we need to take the under root because there is a square on R. This should basically get us 6.83 times 10 raised to 11 meters. Now what you're going to do is, the ratio we need to calculate was RB over RS, so 6.83 times 10 raised to 11 divided by 6.95 times 10 raised to 8, that is 983, which is approximately 1000. So it means Betelgeuse is about 1000 bigger in radius compared to the Sun. Okay. Alright, Nadia, Gatika, Saman, Aman, do you guys understand this?
Yes, sir.
Yes, sir.
Cool. Now, let's go forward then. So I hope you guys understand now what the flow of the questions are going to be, so you can, switch faster. Okay. Now, let me move to basically the part where we're going to learn about cosmology and Doppler's effect and Big Bang and Hubble's law and stuff like that. Anyway, so this section of the astrophysics is about cosmology, and the first thing we're going to do in cosmology is emission spectra. So we've already done this in quantum physics, but in astrophysics it is also needed. All right, so what we need to understand is that elements in a star are usually number one, hydrogen, which basically is the fuel. Number two, helium. And number three, we have could be other gases, but predominantly we are, we look this like majority of star is composed of these two. All right, so 99% like the combination of these two are there. Now, so analyzing this, we can actually see that when basically you see an emission spectra, right? Or yeah, so let me show you. Wait a second, please. Make it gray and make this similar one. Okay, like this. So generally what happens is that in the emission spectra, as you already know, so suppose this one, the first one, is the regular hydrogen spectra. This is the emission one. Okay. Move it here in the lab. So if we check hydrogen, it is going to be somewhat like, right, I just need to this here, and let's move it a bit. No, we should move it even closer. Look at TK, it's fine. Okay, anyway, so now I need to color it a bit. So basically, as you know, emission spectra is all black except for the wavelengths that are emitted by hydrogen, right? It's from when the gas is excited, right? You already know this a bit. I try even. It's easier. Okay, wait. Okay. So, and the bottom one, I'm gonna keep it as the, let's say this is the shifted hydrogen spectra measured from a distant galaxy. Okay, so what happens is, now we're looking at this spectra. What you see is, we see some colors here. The bluish colors first. Like this, and then of course a bit, should be the opposite way though. And then a bit green ones. So these are the colors emitted, okay? And the reddish ones at the end, like this. Now in the lab it looks like this, but what happens is that if you view them from a distant galaxy, you see them as a little bit shifted to one side. Shifted means they are showing higher wavelengths than what they should show for hydrogen. I'm going to give you the idea behind that too. Okay, so now they're like they're showing you a sort of shift to this, because on this side you have you could say they're red wavelengths, and they're like blue wavelengths on this side. So you should know that the wavelength should increase on that side. So for this, what we see is that when we analyze this in the lab, what we see is that the shift are like from one towards the right? So we can say that here lines seem to be shifted towards red. All right, so we should remember that. Now, okay, wait a second, please. Interesting, huh? So why this happens is because when astronomers observe light from distant galaxies, they observe differences in the spectral lines to the light from the sun. Okay. Now, due to the same characteristic pattern, elements can be easily identified. That's how we know the composition of a star, that what kind of gases it has, right? However, it seems slightly shifted. Now, how? Because lines in the spectra from distant galaxies show increase in wavelengths. Very important point. And now lines are moved or shifted towards the red end of the spectrum. All right, so this is what you observe when you see the same element or particular element from a distant galaxy. Do you guys understand this? Any questions, please? Okay. Now basically this brings in the information from AS, and in AS we learned about Doppler's effect. Now what we observe is basically the Doppler's redshift, it is called, in terms of light when you're looking at it. And Doppler's redshift is basically defined as the apparent change in wavelength, just to remind you, remember, or frequency of the radiation from a source due to its relative motion away from or towards the observer. Keywords, please. Apparent change. This highlighter I don't like. Apparent change and relative motion away or towards the observer. Okay. Now, so you should remember that there are two different kinds of shifts that we're going to observe. The first one is the red shift, and the other one is the blue shift. Okay. Now, red shift primarily means that it is basically that object that you're looking at is moving away from Earth. This is why the wavelength seems to be increased, and blue shift means that the object is moving towards the Earth, which means if it's coming closer, then the frequency increases, wavelength decreases. You should know this, right? This can be observed by the spectra. Now, so number one, that basically this is when shift is prominent, when the speed is notable, right? Relative speed, in fact, that's right, relative speed is notable, and shift is observed by the spectra of distant galaxies, as we have just seen in that spectrum as well. All right. Now, they might also ask you a question that define red shift. So if they say that, please do write this formula. The definition is the fractional increase in wavelength due to the source and observer receding. Receding means moving away from each other. So that's the definition. You should remember that. Now, the formula for redshift is Okay, sorry my friends. Okay, now the formula for redshift is delta lambda over lambda equals to delta frequency over frequency equals to V over C. I'm going to explain everything, do not worry about that. But right now, let's move it a bit down and explain this. So this is basically the change in wavelength. This is basically the wavelength emitted from source. This is basically the change in frequency, and that's frequency emitted from source. This is basically the speed of recession. Speed of recession is the same as meter per second, means how fast it is going away from us relatively, and this is the speed of light. All right, you already know this. Now what I want you to understand from this is that, please note that this equation only works for non-relativistic galaxies. Now, non-relativistic means that it is a body moving at a speed much lower than speed of light. Is that clear, everyone?
Sir, what do we mean by shift is prominent when the relative speed is notable?
Because the equation is that the observed frequency is frequency of source times the speed of whatever, speed of light or whatever, speed minus speed or plus minus speed of source. If the speed of source is notable, like it's fast enough, then you see a significant change in frequency. Do you understand?
Yes, sir.
Same goes in this formula. If this speed is notable, then there will be a greater change, that would cause the change there as well. That's why. All right. Now, the AS equation is not going to be used, but this equation is going to be used. So you should remember that, okay? So now I'm gonna just write a question and let's see if you guys can do it. A particle line in the spectrum of light from a source in the lab has a frequency of 4.570 times 10 raised to 14 hertz. The same line in the spectrum of light from a distant galaxy has a frequency of 4.547 times 10 raised to 14 hertz. Get that? Then it says what speed is the distant galaxy moving in relation to Earth, and then comment if it is moving away or towards the Earth. Can you please do it quickly?
Sir, can you show the formula, please?
Kartika, you did not write it? That's too bad. All right. Any answers, please? Hurry up quickly.
So is it 1.5 into 10 raised to 6?
Yes, that's correct. That's correct, Gatika. So basically, what you guys need to do is you need to find the change in frequency, where frequency equals to V upon C. So that's gonna be, change comes out to be, always put the larger value first, okay? because all of these are scalar quantities, we don't need to do final minus initial. And then divide by the first observed one, which is the lab one, right? And then speed, we need to find speed of light is this. From this, you're gonna get 1.5 times 10 raised to 6 meters per second. That's correct. Now, the question, this is not important, this is easy. The question is if it's moving away or towards the earth. So what you're going to say is, so observed frequency is less than the frequency of source, right? So what does that mean? The source is
moving away.
yes, receding or moving away, you can write it, because the wavelength is increasing, right? So this would be the conclusion. Now just remember, write a note here please, that whenever this sort of thing comes, basically when they say about redshift, you say redshift means wavelength of spectral lines increases towards the red end of spectrum. What most of the people do, they make a mistake that do not write it becomes red. It is just the shift, does not become red. Is that clear? So don't be lazy like me. Write the full sentences. Alright. I hope you guys understand this. And now in the probably next week we're gonna finish this for good. So see you. Bye.